Hello everyone, my name is Ned Dimitrov, and today I'll be talking to you about competitive weighted matching and transversal matroids. And this is joint work with Greg Plexton at the University of Texas at Austin. In today's talk, I'm going to briefly remind you of this classical problem called the secretary problem. Then I'm going to introduce you to the online weighted transversal matroid matching problem, which is related to the secretary problem. We'll discuss some background to these problems, and finally we're going to solve the online weighted transversal matroid matching problem together. So let's begin. In the classical secretary problem, we have a single job position open for a secretary, and we're going to interview a number of candidates. So initially, we don't know anything about these candidates. So for example, we don't know how good they are, and that's what these question marks represent. So we're going to interview a random permutation of the candidates, and then immediately when an interview is over, we know how good this candidate is. And then we have to immediately on the spot decide whether to give this candidate a job offer or whether to continue interviewing the remaining candidates. And so the question is, what algorithm should we use so that we can hire a good person for the job that we have? Another way to look at this problem is a problem between bidders and items. So in this problem, we're just trying to sell a single item that we have. This is like the job opening. And then we have a number of bidders bidding on these items. And these bidders are like the job candidates. And of course, initially, we're not going to know the bidders' bids. This is like not knowing how good a candidate is before we interview them. So formally, the secretary problem is as follows. We're originally just given the total number of bidders. Then a uniformly random permutation of the bidders is revealed, one bidder at a time. And when a bidder is revealed, we basically reveal their bid. And when a bidder is revealed, we have to permanently decide whether to match this bidder to the single item that we have, or whether we continue to look at the rest of the bidders. And the goal is to find an algorithm that has expected weight within a constant of the optimal matching. So an optimal matching here is a matching that's optimal given that ahead of time we know all of the bidders' bids. So let's go through a specific example of the secretary problem just to make sure that everybody understands. So here it is. Initially we don't know everybody's bids, but let's also pretend that we don't know the edges in the graph. And I'm just going to color these bidders individually so that I can emphasize that we're interviewing a random permutation of the bidders. So now we're going to reveal one bidder at a time in this random permutation. So let's reveal the first bidder. This bidder is just bidding 1 on the available item. But it's very early on, so let's say that we decide not to sell the item to this bidder. Then we go on to revealing the next bidder. This bidder is bidding 4. It's still pretty early on, so let's say that we want to wait again. So let's move on to the next bidder, not selling this item. The next bidder is bidding 2. That's not so good of a bid. Let's see what the guy after that's bidding. And now this bidder is bidding 5. This is very late in the process, and this bidder is actually bidding something quite good. They're bidding something that's higher than all of the bidders that we've seen before. And so we're tempted to sell the item to this bidder now, and let's go ahead and do that. And that's going to be symbolized by this red arc here. And so once we've made this sell, we're committed to it. So even if the last bidder is bidding 1,000 for the item, we cannot sell the item to the last bidder. So we're forced to not match the item to this last person because we've committed to selling it to the person who bid 5. So this is the secretary problem. Initially, we don't know either the bids or the edges between bidders and items. And what we're going to do is take this problem and generalize it to the transversal matroid matching problem. And the way that we're going to do this is we're basically going to have more than one items for sale. So now initially we're neither going to know the bidder's bids, nor are we going to know what item this bidder is bidding on. So more formally, the online transversal matroid matching problem is as follows. Initially we're just given the number of bidders, and then a uniformly random permutation is revealed one bidder at a time. And when I say revealed, I mean that we're both revealing the bidder's bid and the bidder's connections to the items. In other words, what items this bidder is bidding on. And when we reveal a bidder, we have to permanently decide whether to match a particular item to this bidder. And our goal, similar as in the secretary problem, is an algorithm that returns a matching with expected weight within a constant of optimal, where the optimal matching is the one that's optimal given that ahead of time we know all of the bidder's bids and all of the edges in the graph. So let's see some history behind these two problems. The secretary problem was originally solved by Lindley in 1961, and it has a rich history, and there have been a number of surveys written on it, for example, these two. And one survey writer goes as far as saying that the secretary problem has been extended and generalized so many times that it can now be considered its own field within mathematics probability and optimization. So let's see how our particular generalization works. So our particular generalization is actually a subproblem of the online Matroid problem, which was formalized by Babayev et al. Recently. And Babayev et al. Show that O of log n ratio for general Matroid. So in other words, they give an algorithm that's within O of log n to the optimal independent set in general Matroids. But we know constant ratio algorithms for a number of Matroids. So for example, I've already said that the secretary problem has been solved with a constant ratio algorithm, but we also know constant ratio algorithms for uniform Matroids, bounded left degree transversal Matroids, graphic Matroids, and the truncations of Matroids. So let's see how today's paper, which specifically talks about transversal Matroid matching, fits into this picture. So I said that we have a constant ratio algorithms for a number of Matroids. So we've already seen that the secretary problem is a special case of transversal Matroids where we have a single item up for sale. It turns out that uniform Matroids are also a special case of transversal Matroids where we have the complete bipartite graph. In other words, every bidder is bidding on every item. Bounded left degree transversal Matroids are of course a special case of transversal Matroids where each bidder is not bidding on too many items. It turns out that to prove a constant ratio algorithm for graphic Matroids, you do it through a reduction to bounded left degree transversal Matroids. And finally, the results for truncations of Matroids is as follows. It says that if we have a constant ratio algorithm for Matroid M, then we can get a constant ratio algorithm for the truncation of Matroid M. So along with our results, this gives constant ratio algorithms for truncated transversal Matroids. So let's see a simple sample and price approach to solving the secretary problem, and then we're going to try to take this approach and generalize it to transversal Matroids. So here's the simple approach. The way that it's going to work is we're going to sample the first half of the bidders that come in the random permutation. So in this graph, you can think of everything above this dotted green line as being sampled. Then we're going to set a price for the item, and the price is going to be the highest bid inside of the sample. And what we're going to do is, outside of the sample, we're going to sell it to any bidder that meets the price of the item. And what we're hoping for here is that the second highest bidder is inside of the sample and that the highest bidder is outside of the sample. If this happens, then we're assured that we're going to sell the item just to the highest bidder because we've set a very high price for it. So we get the best match with probability at least 1/4 because with 1/2 probability, the second highest bidder is sampled, and with 1/2 probability, the highest bidder is not sampled. And this in turn leads to an algorithm with expectation at least 1/4 of optimal. So let's see what's difficult about taking the sample and price approach and generalizing it to general transversal Matroids. So I'll show you a couple of examples. First, consider this example where we have a single bidder of weight 2 and then a number of bidders of weight 1, and of course we have a number of items. So suppose that when we sample, we've sampled this bidder of weight 2, and we ask ourselves now, what prices should we set to these items? So remember, in the original approach, what we did is we set the price to the highest in-sample bidder bidding on the item. So if we did this, all of these items here would have a price of 2, which would make sure that we actually don't sell any item to anyone outside of the sample. So this is bad because we're going to be missing more than a constant fraction of the optimal matching. And of course, in this example, I have a single bidder of weight 2, but you can make sure that such a bidder gets sampled with high probability by just replicating that log n times. So this example suggests that we need to somehow have a lower price for the items, because if we set it to the high price of 2, then we're not going to sell any of them. So now let's consider another example. It looks exactly the same as the first, except this very last bidder, I'm going to give them a bid of infinity. So now this is the only bidder that's important to get within a constant fraction of optimal. So let's say again we sample this bidder of weight 2 and then a bunch of bidders of weight 1. If we go with the low price approach, Then we're going to price all of these items at a price of about 1. And then what happens is it's very likely that the single item that the infinite weight bidder is bidding on is going to get sold to somebody else who's bidding very low for it, who's bidding 1, because it's very likely that one of these other bidders are going to come before the infinite weight bidder in the random permutation. So this other example suggests that we need a high price to be set for the items. So it's really this pressure between low price and high price that makes the generalization difficult. Now let's see what happens when you have bounded left degree transversal matroids. With a bounded left degree transversal matroids, what happens is we can make sure that this bidder of weight 2 cannot block too many of the items, because remember, bounded left degree means that they're not bidding on too many items. So with bounded left degree transversal matroids, we get rid of the left example, we get rid of the low price pressure, and we can just go with the high price algorithm, and that's indeed what happens in that algorithm. But since we're trying to do it for general transversal matroids, we have to figure out a different way of figuring out a solution to this low price versus high price problem. So the main idea behind our algorithm is the idea of candidate edges. So we're going to define 0 or 1 candidate edges for each bidder, and we're going to construct an in-sample matching out of these candidate edges. So this in-sample matching is going to be used for pricing. Then we're going to construct an out-of-sample matching using the candidate edges. And this matching is going to be used to figure out what item we should sell to which out-of-sample bidder. And finally, for the proof, the way it's going to work is we're going to relate the out-of-sample matching created by our algorithm to the in-sample matching created by our algorithm, and finally we're going to relate that to the optimal matching. So let's begin just by going through an example of the algorithm, and then we'll go through the proofs. So this is how the algorithm works. First, we're going to fix an order of the items. So let's say that the order we're just going to fix here is highest to lowest. Then we're going to process the sampled bidders in decreasing bid order. We can do this because the bidders are sampled, so we can order them in their bid order. And what we're going to do is for each bidder, we're going to match the highest neighboring unmatched item. So let's do that. So the first bidder that we're going to process in the sample is this bidder of bid 10. So what's the highest neighboring unmatched item? Well, it's this top item. So that's the item to which we're going to match that bidder. So next we process the next bidder, which is this bidder of 1. What's the highest neighboring unmatched item to that bidder? Well, it's the second item here. So we're going to match that bidder to the second item. So now we're done processing everybody in the sample, and we're going to use this matching to set the prices. So we set the prices using the matching, and any items that have been unmatched in the sample get a price of 0. So now let's process the out-of-sample bidders. Now, the out-of-sample bidders, we can't order them in any way because, remember, they're just coming in one at a time. So we're just going to process them in arbitrary order, one at a time. And for each bidder, we're going to find the highest neighboring item with a feasible price. And if that item is not sold, we're going to sell it to the bidder. So let's do that. What's the highest neighboring item with a feasible price that's neighboring this bidder of bid 5? Well, it's this item with a price of 1. It hasn't been sold yet, so we're going to sell it to that bidder, which we're going to indicate with this reddish line. So let's process the next bidder. What's the highest neighboring item to this bidder with bid 6 that's been with a feasible price? Well, it's again this item with a price of 1, but it's already been sold to the bidder who bid 5, so we're not going to sell anything to the bidder of bid 6, even though he was bidding on something that we haven't sold yet. So finally, we process the bidder with bid 12. What's the highest neighboring item with a feasible price? Well, it turns out to be this top item with a price of 10, so that's the one we're going to sell to that bidder. So remember our ideas of these candidate edges. So you can see that these darkened edges here is what's going to be the candidate edges in our algorithm. So just to be a little bit more precise, this is how we're going to define the candidate edges. So if L is a bidder and M is the candidate edges for sampled bidders heavier than L, remember we always have this because we process the sampled bidders from heaviest to least heavy. Then we define the candidate edge as follows. We're going to look at all of the items neighboring this bidder, and we're going to take away any items that have already been matched. And if anything is left, then we're just going to return the highest item. So this is exactly what I've been telling you in English before. This is just a more mathematical way of saying it. Just return the highest neighboring unmatched item. So before I can go on to some of the proofs, let me introduce some terminology. So imagine here we have all of the bidders, and some of the bidders will be sampled, and some of the bidders will be out of the sample. So I'm going to use the letter M to designate a matching, and if I put a star next to the M, it's going to be a maximum weight matching. Matchings created by our algorithm are going to have a little C, and the C stands for candidate edges. And some of the matchings are going to be in sample or out of sample, so I'm going to designate that with some subscripts. So a subscript S means in sample, a subscript O means out of sample. Now if you don't remember this, don't worry too much because I'm going to remind you as I read over the slides, but I just wanted to let you know ahead of time. So this is how we're going to go about showing our proofs. We're going to use two basic properties of candidate edges. The first property is that each bidder has 0 or 1 candidate edges, and this candidate edge is uniquely defined by the sampled bidders heavier than L. Property 2 says that for each sampling S, the matching created by our algorithm inside of the sample has weight that's at least 1/2 of the optimal matching inside of the sample. And remember that the broad idea of our algorithm is we're only going to price and sell using the candidate edges. And the candidate edges in our example, remember, were these very thick edges that we have, and we priced using those edges, and then we only sold using those edges. So this is how we're going to go about our proof. We're going to prove two lemmas. The first lemma compares the expected value of the weight of the matching created by our algorithm inside the sample to the weight of the optimal matching on the entire graph. The second lemma compares the expected weight of the matching created by our algorithm outside of the sample to the expected weight of the matching created by our algorithm inside the sample. And this directly gives the result, because using lemma 2 we can compare out-of-sample matching by our algorithm to the in-sample matching by our algorithm, which then with lemma 1 we can show is within a constant factor of the optimal matching on the graph. So let's go about proving some of these lemmas. So what I have left to show you is proofs of the two lemmas given the properties of candidate edges, and then proofs of the properties of candidate edges. So let's begin by showing you proofs of the lemmas given the properties. Before we begin the proofs of the lemmas, I'm going to introduce this fact that simply says the following two probability distributions are equal. In the first probability distribution, we sample each bidder independently with probability 1/2. In the second probability distribution, we first draw a random number from a binomial distribution with parameters n and 1/2, where n is the total number of bidders that are going to be bidding on all of our items. And then we're going to sample the first k bidders from a uniformly random permutation of the bidders. So using this fact, we're going to be able to get away from this uniformly random permutation of the bidders and just think about flipping a coin for each of the bidders. So let's go on to see a proof of lemma 1. Remember, lemma 1 compares the expected weight of the matching created by our algorithm inside of the sample to the weight of the optimal matching on the entire graph. So the first step is that the weight of the matching created by algorithm inside of the sample is at least 1/2 of the weight of the optimal matching inside of the sample. This was one of the properties of candidate edges. Using linearity of expectation, we can just pull out the 1/2. Now, expected weight of the optimal matching inside of the sample is at least the expected weight of a particular matching inside of the sample. And the particular matching we're going to look at is the optimal matching on the entire graph, but we're going to throw out any edges that are not inside of the sample. And that's what this ind here indicates. This is just the indicator function that is 1 if the edge is inside of the sample and 0 otherwise. So once again, we can use linearity of expectation to pull out the weights. The expected value of an indicated function is just the probability. So now what's the probability that a particular edge is in the sample? Remember, using our effect, we're just flipping a coin for each of the bidders. So the probability that an edge is in the sample is 1/2, which lets us get this 1/4 result and the ultimate result of the lemma. So let's go on to proving lemma 2. But actually, instead of proving lemma 2, what I'm going to do is prove lemma 2, but for every item. So instead of showing that the expected weight of the matching outside of the sample is at least 1/4 of the expected weight of the matching inside of the sample, what I'm going to show is that for any item, the expected weight that the item gets outside of the sample is at least 1/4 of the expected weight that the item gets inside of the sample. So let me first remind you of the properties of candidate edges, and then we can go on to prove that lemma. So the two properties were, first, that each bidder has 0 or 1 candidate edges that are uniquely defined by the sample bidders heavier than L. And the second property is that for each sample S, the candidate edges create a matching on the sampled subgraph. And this other part we've already used in the proof. And just to remind you, the broad idea is that we're only pricing and selling using the candidate edges. So here's a description of the algorithm that we went through just in English earlier. So initially we're going to initialize two sets to empty set. The first is a matching that we keep inside of the sample, and the second is a bunch of edges that we're going to look at outside of the sample. So the first thing that we do is sample some of the bidders. That's all of the bidders in S. And then we're going to process the sampled bidders in decreasing bid order. And what we're going to do is we're just going to look at the candidate edge for this bidder, and we're going to add it to this matching that we're creating inside of the sample out of candidate edges. Then we're going to process the bidders outside of the sample in an arbitrary order. We're going to look at the candidate edge for each bidder, and we're just going to put it in an edge set. So this edge set is going to be all of the candidate edges that are outside of the sample. And then all that we do at the end is take this edge set and trim it down into a matching. So let's see what that means. In this for loop, each bidder can be added to the edge set only once, because they can only be added on that particular step of the for loop, on that particular iteration. But each item can be added multiple times, because it could be on one end of the candidate edge for many bidders. And in this trimming process, all we're doing is throwing out any edges where the item is in the edge set more than once. So what we're going to do now is use our effect to combine these two for loops into a single for loop. So the single for loop looks like this. We're going to process all of the bidders now in decreasing bid order. We're going to take a look at the candidate edge for this bidder, and then we're going to flip a coin to decide whether this bidder is inside of the sample or outside of the sample. If they're inside of the sample, we're going to add it to this sample matching that we're creating, and otherwise we're going to add it to the edge set. And at the end, we're going to do the same trimming procedure that I described to you before. So now to prove lemma 2 prime, we have to argue about the weight that a specific item gets both inside of the sample and outside of the sample. So let me introduce this graphic here that's going to help us visualize how this proof works. So here I've drawn all of the bidders that are bidding on a specific item row in decreasing bid order. In other words, L0 is the highest bid, L1 is the second highest bidder, L2 is the third highest, and so forth. Okay, so now let's see what happens to row as we run through our algorithm. So the first thing that's going to get processed, since we're processing bidders in decreasing bid order, is L0. Now suppose that row doesn't come out as a candidate to L0, so it isn't returned by the candidate function. That means that we're neither going to price nor sell row using L0, so I'm going to indicate that with a black box. Let's say that when we process L1, row also doesn't come out as a candidate. Again, this means we neither price nor sell row using L1. That's another black box. Now suppose when we process L2, row does come out as a candidate out of the candidate function. But this is before we flipped a coin to determine whether L2 is sampled or out of sample. So we know that with probability 1/2, it's not sampled. So I'm going to indicate that with an O over the L2. And the O stands for, of course, out of sample. So let's say that when we process both L3 and L4, row again doesn't come out as a candidate. That's 2 more black boxes. But when we process L5, row does come out as a candidate. Again, when row comes out as a candidate, we don't know if L5 has been sampled yet or not. But we know that with probability 1/2, it is sampled. So let's see what happened. Remember that the broad idea is we only sell and price using candidate edges. And also remember that one of the properties said that candidate edges constitute a matching on the sampled subgraph. So we've already had a candidate edge on the sampled subgraph that goes to row. This is this edge L5, which means that no other later bidder can be sampled and have a candidate edge to row. And it also means that we're going to set the price to row to L5, which in turn means, since we're only selling using candidate edges, that the only person outside of the sample that can possibly purchase row is L2, because that's the only person who is out of sample and has a candidate edge to row. So basically what happened is that with probability 1/4, row gets sold to the heaviest candidate. So this is exactly what happened in the secretary problem. We're hoping that the second highest bidder is inside of the sample and the highest bidder is outside of the sample. Here we're hoping that the second highest candidate is inside of the sample and the highest candidate is outside of the sample. So this is what gives us our 1/4 result and proves lemma 2'. So let me just give you a little bit of extra intuition on how we can go one step further in formalizing this proof. So imagine here all of the unrevealed randomness in the algorithm that we have. So these are basically n bit flips, one for each bidder to determine whether they're in sample or out of sample. And what happened is we revealed a prefix of this randomness, beta, up until row came out as a candidate for the first time. And then what we can go on and do is argue that all of the continuations of beta up until a full length of n bits, for about 1/4 of these extensions, row is connected to the first candidate. And this is true for all prefixes beta. And this is how you can go on to fully formalize the proof. So let me remind you again of the two lemmas that we've shown. The first compares the in-sample matching created by our algorithm to the optimal matching, and the second compares to the out-of-sample matching created by our algorithm to the in-sample matching. And these two lemmas are enough to give us our constant ratio result. So I still have left to show to you proofs of the properties given of the candidate edges. However, I'm going to leave that for you to read in the paper. So let me summarize what we've seen today. I've shown you today a constant ratio algorithm for the online transversal matroid matching problem. And the algorithm that I've shown you actually generalizes results for the secretary problem, for uniform matroids, for bounded left-degree transversal matroids, and graphic matroids, because all of these in one way or another are a special case of the transversal matroid. Furthermore, along with the reduction to truncated transversal matroids, our algorithm provides a constant ratio algorithm for the truncations of transversal matroids. But let's see some failings of our algorithm. So one of the main motivations to look at these matroid matching algorithms is online auctions. And in particular, we want to create truthful mechanisms for these auctions. So let me show you that our algorithm doesn't actually lend itself to this truthfulness property. So suppose that we have this situation where we've sampled the single bidder of bid 10, which sets the price of this top item to 10 as well. Now let's consider the incentives for this second bidder. If this bidder is truthful, then what we end up doing in our algorithm is selling him the top item at a price of 10 and a total utility of 1. However, if this bidder lies and says that their bid is actually 9, then we end up selling them this bottom item at a price of 0 and a total utility of 11, which gives incentive to this bottom bidder to lie. So this is an area for future work. So here are some future directions. Of course, one of the major future directions is, can we get a constant ratio for the general online matroid problem instead of just a specific transversal matroid problem? The second question is, can we get a different algorithm that actually lends itself to truthful mechanisms in this transversal matroid matching? And finally, can we really work on these algorithms to get the constant factors good enough so that they can be good in real online auction applications? Thank you very much for listening.